Hello, today my topic is about the RFIC module design tool, and it's the oscillators. So the first part is the introduction of the oscillators, and it's the advantages of the MMSE-based oscillators. It has high operating frequency and excellent repeatability and reliabilities, and it also has hybrid solutions. High integration level enable new applications and cost effective for high volume production, and it eliminates tuning in production phase. And for the oscillator basics, it generates a periodic signal using positive feedback. At least one active device in the loop is the device is amplifier, and the oscillation sustained by feeding output back in the phase. And for the oscillator classification, it's based on the frequency, tuning range, noisy performance, or output phases. The continuous time is resonance based the LCDR, and the differential or non-resonator based. The resonator type oscillators use the high linearity HBD technology. And for the oscillation conditions, the feedback approach is the loop gain equals 1 and the total phase shift equals 0, and the negative resistance approach is like the negative resistance cancels losses for the oscillation and startup. And the noise in the oscillators is it's about the it's mainly from the right noise. Is like the thermal short noise or the flicker noise. The flicker noise is from the transistor origin, and one is the phase noise. It's like the frequency domain, and the jitter is the time domain. These two domains are key performance metrics. And for the advanced nonlinear and perturbation method was needed for the accurate phase noise modeling. Then it's the LC oscillator design, and here it's the picture we can see. It's the RF oscillator design flow, and decide the configuration, and then the workers select the transistors, and then it's design the bare circuit current or voltage, then and the feedback from the network, and then it's the resonate design. So target for the cool band satellite LNB application using the HBD process, and it designed and simulated in the Allegient EDS using the VBSE model and the series feedback topology, and to generate the negative resistance and the compensate the tank losses. And the key specifications of this one is it has the excellent phase noise. It's like the negative one more than 100, and the die size is the 700 micrometer by 830 micrometer. And about the frequency drift is the delta 30 megahertz, and the output power variation is the delta 3 dBm. So the main features about the design is it has the high Q square inductors, and the Q value and almost equals 15, and the MMI capacitors, and the semi-insulating, and it's the substrate for the RF performance. So the layout using the cadence and virtuous with the two metal layers and the air bridges. So no additional reactive output network needed due to the sufficient power. So, and finally it's about the temperature compensation. And compared between the compensated and the uncompensated design, the VCO version includes the temp compensation via the bears and the feedback adjustment. And so through all this flow, and finally we can get the final design. Then it's the MMIC VCO fabrication measurement. We can see our measurement setup is the supply voltage is 3 voltage, and the current consumption is 9 ME. So the measurement tools use the probe station and the spectrum analyze. And about the loss, it can be low to the 2.2 dB. So the performance summary, it's like it has excellent frequency stabilities. So here is the picture about the fabricated MMIC oscillators, and this one has excellent frequency stabilities and the wide tuning range with the low phase noise, and it also stable over the temperature thanks to the combination components. And then it's about the high power HBD PA overview, and why we use the DRO. And so the first reason is it has a high Q, and it almost equals the 15, and it has a low phase noise, and also near the 0. And previous we talked about it. It's about 0 phase shift. And let me see it. Okay, so and it has a good temperature stabilities, and so for also the size is very compact, so it's cost effective, and it's very ideal for the fixed or narrow band tunable applications. And for the mode, it also uses the TE mode, and the coupled to the microstrip was magnetic field interactions. So it requires the metallic shielding to increasing the Q value and minimize the radiation loss. And the key material properties, it has almost 3 main properties. The first one is the temperature coefficient, and the second one is unloaded Q factors, and third one is the dielectric constant, and the final one is the field distribution, like the electric field and the H field. And for the electric field, it's concentric around the Z axis, and the H field is perpendicularly to the microstrip plane. So the functions as a reaction cavity when the adjacent to a microstrip line. And then it's the choice of the topology and the VC and drawn design overview. And so first we can see the picture, the macro and prograph of the fabricated dies, and we can see it's the final design. And for about the many types of the DRO topologies, the first one is the reactions type. It's the free-running oscillators and stabilized by the DR, and it has the high superior content and the poor phase noise. And the parallel feedback and the transmission type is the DR between the two lines for the loop feedback, and it has a complex to the model, so it's very difficult to tune the middle bench or the side bench. And the reflection type is we used here. It's like the DR near the microscope line, and it's the unstable amplifier input, and it uses the machine. It's use the design. It's the VCDR and design, and it's easier to modeling and reduce the spares. So the effects phase stabilities and power it's mainly about the more tuning dots, and it has the wider range, but if you want the wider range, you need to decrease the Q and the Q factors, Q values, and increase the noise. So about the modern performance, we can see the Q almost equals 3000, and the simulation shows the notch at the 10 GHz. So about this structure, and I summarized some keywords or the key properties. And for the oscillator core, it's on-chip common based the HBT structure with the series inductive feedback. And for the tuning element, it has 3 on-chip base collector junction diodes. So for the DR placement, the off-chip DR placed near microstrip line for the reflection mode operation. And finally, it's the design trade-off. Trade-off is that means you cannot get all the thing better, all the thing best. You need to give up something like that. That means if you want to the stronger DR coupling, and you need the lower Q value and worse FM noise, and like that. And then it's the differential VCO with the frequency tripler for the cool band LNB. So for this table, it's the summary of the measurement results from the textbook, and we can see here is the parameters of like the supply voltage, current consumption, and the tuning voltage, oscillation frequency, and so on, and output power and phase noise. And we can see the phase noise is -100 to the, so the frequency multipliers basics used in the wave system to up-convert LO signals, and and the active multipliers offer lower conversion loss than the dot taps, and the clipping effect is the dominant mechanism for the harmonic generation. And the second one is the multiplier analysis method, and it has the 2 methods. One is the nonlinear and transconductance model, and then it's the piecewise linear transconductance model. And the third one is the multiplier design consideration. And for the fourth, it's the differential VCO core and with the tripler. And for the detailed introduction, I will skip this one, and then finally I will talk about the benefits of the design introduction I talked previous. So the first one is the low noise. I talked about many times, the low phase noise and the high output swing. And finally, it's the differential output for the better common mode noise rejection. So that's all about the introduction and the properties of the cool band LNB. And that's all the presentation for this time. And thank you for listening and watching.